Okay, so welcome everyone. It's and first of all, thanks to the organizers for having me. It's really nice and nice to see we almost filled up the room. My name is Jørn Bersvendsen. I'm going to talk about serialization in C++. I work at Applica Consulting, and I have been using C++ for about 15 years, mostly in computer vision and robotics, medical image analysis. But for the last year and a half, I've been involved with Kongsberg Defense and Aerospace. And my team is responsible for the navigation system on military vessels. And specifically, we work with distribution of navigation data between numerous sensors and subsystems. As you can imagine, on a big military ship, there are a lot of sensors, a lot of systems, redundancy, and everything. And being quite new to the kind of defense industry, I was surprised to learn that it seems to me that every manufacturer of some military equipment basically makes up their own data format without thinking about any kind of standards. And I assume that there is good reasons for this, but I'm not sure why. And sometimes these data formats can be really like exotic, and we have to read and write hundreds of different data formats or data messages in many different formats, and we cannot control exactly these formats. We just have to implement them. And so a key component in that is serialization. So what is serialization? It is the process of turning C++ structures into sequences of bytes. And then going back, which is normally called deserialization. And you would do this to store. Let's say you have some struct and you want to just save it to a file, and then later you want to reload it, or you want to communicate it with some other subsystem, send it over the network, do like a remote procedure call, and various other reasons. So yeah, you have some kind of a struct. I see the projector is not liking my dark theme, but hopefully it's readable. And you want to turn it into some kind of serialized representation. And there are kind of two different categories, depending on whether you care about the specific data format or not. So you might not care about the exact bytes in your data stream. You just want to be able to save it and then load it back later, or send it to someone else that is then able to load it. So the first example is like a binary representation. And you just care that the data format is nice and compact and everything, but you don't specifically care about the bytes as long as you are able to serialize and then deserialize. Or you may be in a different situation where you actually are serializing to like JSON or XML, or this last one here is NMEA, which is a common format in marine environment. So those are kind of two different categories. This is not a new problem, and there are a lot of libraries out there. I'm not going to give kind of a deep dive into this, but I'll give three kind of general categories. So first is a set of libraries that are general purpose C++ first libraries, and these focus mostly on the usability and performance. And they're primarily designed to be saved and loaded with the same library. So Boost has a serialization library. There's a library called Serial, which I have used quite a bit, and I can absolutely recommend. Also CPP bits, which is zero overhead, slightly more modern maybe. Then there is a category of libraries that are like cross-language data interchange. So things like protobuf and flat buffers, where you focus on a schema and you kind of define your data message in an intermediate language, and then you process that to basically generate C++ code that will handle the serialization and deserialization for you. The benefit, of course, is that you can then generate the same code in Java or whatever other language you use. And there is message pack, which is schema-less. It doesn't have this intermediate language, but it has a very specific data format that has implementations in many languages. And the other kind of end of this spectrum would be a library that is completely specific to a specific data format. So if you're just going to serialize with JSON, there is a JSON library, many. If you're just going to do XML, there are XML libraries and so on. None of these really fit all of our requirements. So what we wanted in our team was something that had excellent usability for C++, and we use C++20. We don't really use a lot of other languages, so we didn't need inter-language data exchange. We have to support multiple data types, data formats, and it has to be easy to add new ones. And also, we need specific control of the data format. So we have some strange binary representation, some like odd-sized integers, some bit fields, and I'll get back to some of these. And the kind of key requirements for us is usability and control. So we want something that is really usable, nice looking in C++, and also get really fine control of the serialization. And what I mean by usability is, so this is an example. We should be able, in an ideal world at least, to have something like this where we have some enums, we have some structs that are like nested structs, we have some std vectors. And at the end, we should be able to have some instance of this essentially arbitrarily complex structs. And we should have a single save function that just takes that value and saves it, in this case, into a JSON, some JSON archive. And this should kind of just work without writing any specific serialization code to any of our structs in an ideal world. And this is not always going to be possible, but in some cases it will be. So I'll show you a little bit how we kind of structured our library and implemented this. So first of all, we have the archive, and this is an approach used by many other libraries in serial, boost serialization, and others. And the archive is essentially responsible for taking C++ types, or a subset of C++ types, and storing it into some data storage. And I've kind of skipped over the data storage here. In the simplest case, it's just a std vector that you are pushing back to, or it could be some file stream. But the archive's job is to take some set of known values or value types and push it into the archive, or load it from the underlying storage. And you may have multiple different archive types. So you may have the binary archive, and you may have a JSON archive. And for the binary archive, you don't care about the names of the fields necessarily, but for JSON, you do care. And different archives are going to support different types natively. So the binary archive, for example, might not natively support a std string, but the JSON archive might do that. So that is one end, if you will, of the library. So that's responsible for pushing into the underlying storage in the correct format. And the other end would be some save and load templated functions at the kind of top level. So save would be a function that takes an archive and some value, and it saves that value into that archive. So if you gave a JSON archive, it's going to save it in JSON. Give a binary archive, it's going to save in binary. And similarly with load, you just give a reference, and the job of that load function is to load from the archive into that value. So for example, if we have a point struct with the XYZ floats, we instantiate a point, we have a binary archive, and we should be able to call save and give the archive and the point. And the archive doesn't know how to save a point. We haven't written any code specific to our point to serialize this. So this should still be equivalent to calling save on the archive for X, Y, and Z in order. And similarly with load, we should be able to load. And in our save and load functions, we're not going to write any specific code for this point class. But we still want it to work. And it should work for arbitrarily nested types. That's the ideal scenario. So it's not always possible to get there, but so as a kind of a stepping stone, we're going to introduce this serialize method inside of the structs that we want to serialize. And I'll show you some case where you can actually get rid of this, but in the general case, you're going to need something like this. So in this case, we have a serialize method, and we just get in, it's a template, and we get in some archive value. And that archive value is going to have a call operator overload And so we just call that archive for all of the data members that we want to serialize. And when I say serialize, I mean both save and load. So depending on what you give in to the serialize method, you can get different behaviors. So you have this this save facade, which is just a tiny little bit of wrapper around some archive. And in its call operator, it just calls save. And you can have another one, which is a load facade, which does the same thing, just calls load. So then you can reuse the serialize method to either save or load, depending on what you give it in. And you can also add other things here as well. So you can add, like you can have a little bit of a facade to just write to log, or just do other things specific to your needs. So again, I'll show you some cases where you can get rid of this, but for now, let's consider we have this serialize method is essentially just a way of visiting all the data members. So we need to implement save and load, and what we can do is we can we have a save, and it takes in an archive and a value. So the first thing we do is we do an if const expr requires, where we simply ask the archive, or we ask the compiler, can this archive save this value type? So if it was a float, for example, the binary archive may know how to serialize floats, and then we just do it. Otherwise, we are going to fall back to this serialize method inside of the struct. So we just make this little save facade around our archive, and we call serialize on that value. And internally, then it is going to call that archive for all of the data members. And that save facade is then going to call back into save. So it's going to recursively do all of the data members. So if you have structs nested inside of each other, it's just going to recurse. And load is the same. You just give a load facade instead. And so already with this very small amount of code, you can get some nice initial results. So if you have a point with the x, y, z, and you have this visitor serialize method, and you have this triangle which has 3 points. You can make a triangle and a binary archive, and you can call save. And what it is going to do is basically going to save the x, y, z on all of the 3 points. And we didn't have to write specific code for doing that, except for this serialize method. And load would do the exact same thing. So in load, this would just be a mutable reference, and it would load back into that struct. Now, different kind of libraries have different flavors of the serialize method. So some libraries use a macro. You can use a macro for this. So you just have a macro, give all the field names, and then that basically generates the serialize method for you. I don't quite like this macro, but if you're going to have a serialize method, you can have this style where the archive accepts any number of parameters, and it just calls save and load for all of them. It's a little bit more succinct, but you don't get the names of the fields. So if you're saving to JSON, you want the names of the parameters there as well. And also, you can't really customize how all of these fields are serialized. So to get around the kind of the lacking of the field names, you can do some kind of macro where you do like a named or name value pair or something. It's not really pretty, but it's possible. What we end up doing is actually just providing the actual names of the data members, and any of the others will work. But this is quite nice because you can separate the names of the variable in C++ and the name of the value in JSON or XML, which might not always be the same. And additionally, you can then pass different additional arguments to this call to the archive. And that we will use to kind of control the exact behavior of the serialization. And just quickly so this is the last style is what we use internally, but yeah, you may use some other style if you desire. And just quickly, there are other ways to put the serialize method. You can have it inside the struct, you can have it outside, And you can also split with save and load. So if you really want to do something different when you save versus when you load, for whatever reason, you can do that. All right, so we need a couple of extension points to kind of control the serialization. So the default behavior that you're going to get is not always going to be what you desire. So for example, let's say we have a list of points. We have a std vector of points. Each have like x, y, z coordinates. We make a JSON archive. We save those points. The default behavior that you're going to get is what you see here, which is just what you would kind of expect. So it's a array in JSON. But this might not be the way that this is encoded in your particular data format. So for example, you may have this, where you have just a vector of a list of 3 values, and each of those is a point. You may also have like just a single large list of values with x, y, z, or you may have a list of strings where each point is encoded as a comma separated list. Or you may even have like parallel arrays of x, y, z. So you can, when you don't really control the data format and you have to just conform to it, but you still want the C++ code to read nicely, then we need some extension points to allow to overload that default behavior. So we have a couple of these. The first one is I'm going to show is the serializer. So we just in the library we just have a empty templated struct called the serializer, and it's templated on some archive type and some value type. And in the library itself, it doesn't do anything, but it allows the user to overload the behavior of the serialization for specific types. So in the user code, you may have a specialization of this serializer. And if we wanted to store this point as a vector of 3 values, we would, in the save, we would just convert it to a std array and then save that std array. And in the load, we just load a std array and we save all of we load the components from that std array. So that's one way of kind of controlling on the type level how values are serialized, and you can partially specialize this serializer as well. Yeah, so to add support to this for our save and load method, we're going to add a new check. So before we check whether the archive natively supports this type, we first check if the user has given some specialization of this serializer struct. And if the user has given this specialization, that kind of is the first priority, and so we use it. Otherwise, we check if the archive supports it. And the same with the load. Now, another kind of way of controlling how serialization happens, we have the default serializer. So this is something that the library ships with. So some cases have good defaults across many different libraries, many different archive types. So for example, if you have a binary archive and we have a fixed size array of 5 things, you probably just want to save all of those 5 elements and then load just 5 elements and not do anything more. And std optional and some enums have other kind of good defaults across a lot of different archive types. So it makes sense to ship that with the library. So as an example here is how we can do std array. So we have this default serializer, and in the save we specialize this for std array. Yeah, there's a typo here, but yeah, we specialize this for std array, and for each of those elements we just save them, and for each element we load them. So that means that all binary archives are going to support std array, at least this version of it. So for enums, it also is something that has kind of a good default. You can overload it if you want to, but I think what is most common is to just store the enum as the underlying type. So you save that as the underlying type, and then you load it back. So in the save, you just convert it to the underlying type of the enum. You save that, and when you load, you first load the underlying type, and you convert it to the enum. Now, you could use something like magic enum. So if you don't know magic enum, it's a very nice little library that uses some non-standard C++ to actually some essentially compiler intrinsics to give you things like looping over the values of an enum and the names and converting between an enum and a string, things like that. And you can add that in to like check at runtime whether the loaded value is actually a valid enum. So magic enum is it's using some non-standard, so it has some limitations, but it is supported on like MSVC, GCC, Clang, and probably others as well. All right, so so this serialized method is kind of it's okay, but ideally you wouldn't have to write this serialized method in all your structs. So the question is, can we get rid of it and just in a general way iterate over the data members of a struct? And in the general case, the answer is no, but in some special cases, it is possible. And it is possible if the struct is what's called a simple aggregate. So that means that there are no constructors. All the data members are public. There are no base classes and no virtual member functions. So it's just like a plain struct with some data. And in that case, it is actually possible to write something that will give you this, where you can actually iterate over the data members of the struct. And and this is before reflection. So of course, in C++ 26 we will have reflection. For some of us, it's going to be quite some time until we can actually use it in production. So it's nice to be able to ship this code right now. And there is a way to do this in kind of standard code, which will work, but it doesn't give you the names of the fields. So if you're serializing to like a binary archive, you just want to save it and load it, that works fine. And it's standard and nice. But you can also get the field names if you use a little bit of some non-standard C++. But for now, let's consider if we don't need the field names. So I'm going to show you, there is a library that I will show you how you can do this without writing this code yourself. But when I first learned about this, I was a little bit surprised that it's actually possible to kind of iterate over the data members of any struct without writing any specific code. So I'm going to show you how it's implemented, but you don't have to implement it by hand if you don't want to. So if you knew the number of the number of fields in some type, then you could do this. You could do a structured binding. So you do a structured binding. If you know that there are exactly 3 data members in this struct, we do a structured binding, get 3 values, and then we serialize all of them. So whether we're saving or loading, that will kind of just work. Now, of course, not all structs have 3 data members exactly. So what we want to do is we want to write this, where we do a structured binding into a pack. So we just say, just unpack this and let's get some pack, and then we do a fold expression. So we serialize everything. This isn't possible in C++ 23. You're not allowed to have this struct here. But it will be possible in 26, C++ 26, because of this paper. So this will be valid code. But there is still something we can do today. If we find out a way to figure out a way to get the number of data members of this struct. So if you knew the number of data members, and we also knew that there was some, we can put some limit. So let's say I know that I'm never going to have more than 300 data members in my structs that I serialize. We could just do a bunch of if const expr. So we can just check, is there 3 data members? Then I'm going to do a structure binding with 3. I'm going to serialize all of them. And you can, of course, make this recursive, so you don't have to write all of these 500 if statements, but this is the kind of concept. So you could do this. You can just get the number of fields and then have a separate if const expr for each. And this is going to be at compile time. You figure out which if you have. But how do you figure out the number of fields in a struct, or in an aggregate, I should say? You could think that you would be able to do it like this, where you basically do the same thing with the if const expr requires. So you kind of ask the compiler, would this be possible? Could I do a structured binding like this? And if so, then there must be 3 data members. But this isn't valid syntax. You cannot put this structured binding inside of the requires clause. So if you cannot do it on the kind of the structured binding side, you can use the fact that aggregates or simple aggregates don't have user-defined constructors. But there is going to be a constructor defined by the compiler. So if you have 3 data members, you're going to have a constructor which accepts 3 parameters. So you can do this, and this is I got this specific code by a library called CPP bits. And the idea is to check if the number of arguments in the constructors. So first of all, you have to do it in the reverse order, because if you have five data members, you could be constructible with just 3, and the rest would be default constructible. So you have to start with some large n and then kind of work your way down. But you don't know the types of the data members. So what you do is a little bit of a trick. So we have this any. It doesn't do anything, but it is implicitly convertible to any other type. So that if you had a T and it had 5 data members, and it didn't have user-defined constructors, then it would be constructible with 5 any's, because whatever the type of the first data member would be, any would be convertible to that implicitly. So you could do this to actually check at compile time. You can get the number of data members. And of course, this is a huge set of if const export. You can do this recursively, so you don't have to write or unroll all of this loop. But that's the kind of general idea. Now, of course, this will work. It's standard and it's nice, but we don't get the names of the fields. So if we do like JSON or XML, then you still have to do something more. And it's not possible in standard C++ prior to reflection. So it's not possible today. But there is a little library that you can use to help you. And I'm sure there are other libraries as well, but Boost has a library called PFR. It's a header-only library for kind of basic reflection. And it uses some vendor-specific macros that are not standard, but they're supported in like GCC, MSVC, and Clang, at least recent editions. And it will use those kind of vendor-specific macros to parse out the names of the fields. And it will work the same way as I just showed you for simple aggregates, so it will iterate over the data members. And again, once C++26 is available, you can kind of replace this code with our standard reflection. So in order to integrate this, it's actually very simple. We have this default handler, and we just say that for all the aggregates, we're going to have this save. And if you use Boost PFR, you get this kind of magic function, which is called for each field with name. And you just give it anything and a lambda, and it's just going to call call that lambda with the name of the field and the reference to the field. And again, if you don't care about the names of the fields, then you can use an approach which doesn't rely on kind of these vendor-specific macros. All right, so far we already have some good results. So we can have this code right here. We can have enums and structs, and without writing any code specific to any of our types, we can serialize this to JSON and anything else that you want to implement. But that is just half the story, because we need to control the data format as well, more specifically. I've showed you how you can do it with types, so you can overload how this point is serialized, but that's not enough. The type isn't everything. So we need to control the exact format that is serialized. So in our team, we have a lot of these binary archives or binary data formats. And sometimes they can be a little bit complex. This is not really a complex example. It's just a kind of a regular example. So we have 16-bit words. And the first one is what we call a bit field. It essentially has a couple of bits that are like Boolean values. Then you have like an enum, which is encoded like 3 bits, and we might have another enum, which is 5 bits, and so on. And these may not align with the byte boundary. So, yeah. And then you also have this kind of temperature. So this is this kind of made-up sensor has a range of 0 to 100 degrees, and they decided to encode that not as a float, but as a uint16. Where 0 is 0 degrees and FF would be 100 degrees. So if you were to use or kind of use the library that I showed you so far, you would have something like this. We have like sensor data, you have a uint16 temperature, and this is encoded so that 0 is 0 degrees, FF is 100 degrees. And you can write the serializer, or you wouldn't have to in this case, but you could write it like this. But then you probably end up having to write getter and setter functions, because this uint16 isn't what you want to have in your C++ code. It's like a value that you cannot use it for anything meaningful without knowing exactly how it is encoded in a specific data format. So you would write something like a getter, where you have a get temperature. There you would multiply by some factor. And a setter, where you take in this temperature. You first have to check that it's in the valid range, because if it is outside the valid range, that is not actually representable in this data format. And then you would divide by the same factor that you multiplied with in the getter. And finally, you cast it down to uint16. And if you have like 100 different data members of this will get tiring really quickly. And this is just a nice example or a regular example. So you want to do something better than this. So what we can do is we can add library support to when you are serializing. Notice you now have a double. So this is the type that you want to have in your C++ type, so that you can actually use it for something. And then when you are serializing, you can add other parameters that tell you how you should serialize this thing. And this is the kind of the verbose version, but it would mean you have the temperature here. First, you check the valid range when you are serializing, and then you are multiplying with this factor, and finally you cast it down to the proper range. And the nice thing is that this will then work for saving and loading. So when you load, you do the exact opposite. So you load a uint16 from the archive, divide by this factor, and then you still check the valid range. And if this was a common pattern in your code, like you have hundreds of these, you can write a single helper struct to do all of those 3 things. And you can just say that you can call it like a fixed size of this type and give it a valid range. And if that is meaningful to your data formats that you're using, it's really nice. Instead of having like 100 different getters and setters, you can just declare it like this. So it becomes like a declarative version instead of having to write a lot of code. So these, we call them specifiers or transformer objects. And they transform an object between the desired C++ representation and the required serialization representation or serialized representation. So again, in this case, you want to have the temperature as a double because that allows you to do calculations and logging and everything. But you need it in this uint16 for to actually communicate with the sensor or the subsystem. So some simple cases would be like factor, where you when you save, you multiply by the factor, and when you load, you divide by the factor. Same with the offset. But actually, these transformers may change the type being serialized. So, for example, we have this hex string. So we have some interfaces where you actually require to format ints as hexadecimal strings. And that means that when you are saving, you are kind of transforming between an int and a string. So the save, in this case, would just format it as a hexadecimal string. And when you load, you then load into the type. So you're changing the type as you are serializing. So when you, again, save, you turn an int into a string, and then when you load, you have to then load the actual string and then turn it back to an int. So in this case, you could do what's over here. You can have like a comma-separated value archive. Give an int. You say that this should be a hex string, and then you automatically get the save and the load, and you don't have to write that specifically. So in order to add support for this, we have to extend all of the save and loads. So we're going to add any number of arguments to the save and the load. Similarly to the serializer, you can add that there as well. And to implement this, we again use this default serializer, and it's slightly more complex now. So we have the archive, the name of the field, the value, and the first of potentially many specifiers. So this might be the value, the t might be an int, and this first specifier may be this hex string. So we just first call save on that specifier. So we take that int, we convert it to a hexadecimal string, and we got some converted value. And then we just save that, in that case, a string. And we give all of the rest of the arguments there. So if there was a long list of these specifiers controlling the serialization, we have just kind of used the first one, and then we pass along the rest. And it just recurs down until there is nothing left. So we take the temperature, for example, we push it through this valid range. That's not going to change the value at all. And then we multiply by this factor, take that value, and we kind of continuously go on until we are at the end. And whatever we have left, we actually save into the archive. All right, so for the load, it's just very slightly different because the type may have changed. So in the case of the hex string, what you have to load is a string, but what is in C++ is an int. So you have to then figure out the type that you have to load, and the type that you have to load is the same type as you saved. If you were saving, you would have gotten a string, and so we have to load a string. So we basically ask the compiler what would have been the result if we were to save at this point, and whatever that value is, it is the type that we have to load from the archive. And then we load that type, and we convert it using this specifier. So one example is like an odd-sized integer. So for example, this temperature may have been encoded not as a uint16, but as a uint24. And a 24 uint, it doesn't have a native C++ type. But you can still do it. So you can say that, well, I'm using the kind of the verbose version here, but you can say that this temperature, when you serialize it, you first check the valid range, then you multiply it by this factor. You cast it to a uint 32 because that's large enough to hold the 24 bits, and then you serialize it as a 3-byte int, which again doesn't have a standard representation. So yeah, so to implement this, I'm not going to go through everything, but the idea is then you just convert it to a std array of bytes, and this is kind of an implementation that does a big endian on a little endian system, but you can check that at compile time or runtime. So in the save, you make this array type of the number of bytes, and you just do all of the bit kind of fiddling to get that array, and then you save that array. And when you load, you do the opposite. Now, one thing that we have used quite a bit is like base64 encoding. So you may have a sensor data that has some, like it might be a JSON, for example, but internally it has a base64 encoded value, or a std vector, let's say. So instead of writing a separate getter and a setter, or like a separate base64 decode there and an encode here, you can just declare that this, when you're serializing, you can just say that this is base64 encoded. So in that case, you would get the first data, which would just be the raw vector with all of the values. And then if you specify this base64, base64 is just a very simple struct, has a save and a load. And in the save, you just convert it to a string of the base64 encoding. Yeah, we have embed, which is when you have, so for example, this case where we have a point that you want to store as a comma-separated list of coordinates. And in that case, you can do embed, where you give some archive. And when you are serializing, that just means you make this archive, take this value, put it inside of the archive, and whatever is in that archive is what you are serializing. So in this case, you take this point, you make a little CSV archive, you put that point in there, and it is going to then generate this string. And when you load, you do the exact same thing, just in reverse order. So you kind of load the std string that you would have saved, and then from there you put out this point. And you can use this in combination. So for example, you may have a JSON which has a base64 encoding of some other binary representation. This shows up sometimes in our code base. So you can then have just your binary data. You can do all of the things that we talked about. So you can specify exactly how this is encoded, or you may not need to. And then if you then write, you take this binary data. When you serialize it, you first have to embed using this binary archive, and then that binary output is going to be base64 encoded. And it's really nice to just be able to write this and have it work for save and load without actually specifying all of this, writing this code by hand, essentially. So for bit fields, it works quite similarly. So bit field again is just essentially some, let's say, a 16-bit word, and there are a lot of values defined on that word. And you can just write in your serialize, you can make a bit field, and that is essentially going to do write a mini archive. So you specify how number of bytes of the underlying storage. And then you get a bit field, which is essentially the same thing as an archive. So you can have the exact same support for like enums and these fixed size ints and everything. The only difference is that you specify the number of bits. So in this case, we have a bit field with like 6 bits of this status enum, 2 bits of this mode enum. And all of that is a single byte. And then what we actually load from the archive is this single byte in this bit field. Yeah, and another example is std chrono. So we have a lot of these type conversions. So std chrono, what you want to have in your C++ code might be like a system clock time point. But what is actually stored in the data format is like, could be nanoseconds or milliseconds or microseconds since epoch. So you can just say that this timestamp should be saved seconds since epoch. And you don't want to have, like, to modify this type. You don't want to have like a separate type for the timestamp just to be able to control the serialization, because different data formats may require different ways of saving this particular timestamp. We also have this one, which is a millisecond since midnight, which is a kind of a strange way of representing timestamps because it only lasts for 24 hours or less. Yeah, it's possible. Yeah, so unit conversion, similar story. So we have internally a unit library, but you may use others. So the type or the unit that you are using when you are in your C++ world might not be the same unit as you are serializing into. And in that case, you can just specify a converter. All right, so we have quite a few of these kind of conversions. So we have a lot of this fixed size formatting. So a lot of our formats are ASCII based and require like a specific number of decimals. So you can just, instead of writing the getter and a setter and everything, you can just declare that this is how it's supposed to be formatted. And same with the hex string. We have fixed mappings, so you can specify a mapping between some value, like could be a string or something else, and then to a set of fixed values that are stored. And we have integers with sign bit instead of using 2's complement, and a lot of these kind of different cases. Also checksums, you can add like a function that is calculated on all of the data that you have serialized so far. All right, so yeah, in summary, we kind of get these nice results where the simple things are still simple. So you can have this code right here. And if you don't need to do anything special with your foo, let's say you just want to serialize the colors and all this to the vector, you don't have to write any specific code for that. But if you wanted to, like example, have this payload here as a base64 encoded value, then you have that opportunity. And this is all the serialization code you need to write. Anything else is kind of general in the library, and you can get this nice JSON. All right, I see I'm a little bit fast, so I'm actually done there. The slides are available, and yeah, otherwise you can just come talk to me. So yeah, are there any questions? Mm-hmm.
We still have the possibility to do it outside of the script itself, because to me it brings coupling in between the serialization code and the type itself. I would prefer to see it outside.
Yeah, you can definitely do that. So you can have the serialize. So I showed you this in the save and load. You do like a if const export requires, you check for this capability and then you check for the others. And that's quite a nice way of giving different options to control. So you can definitely have like an if const export, you check if there is a serialize method for this specific type outside, then you can do it. And that's a really nice way of kind of controlling, because sometimes there are multiple ways of serializing. Like the archive may know how to serialize your struct, and then there might be some other way of doing it, which is like shipped with a library, but you might need a third candidate. So you, in that save and load, you can do like if you have this capability specified elsewhere, you can do that. And if you have like 100 different fields, and just one has a very special, it needs a special handling, you can change the type of that specific fields, and then you don't have to write any of these serialize. But then you kind of sacrifice a little bit because you are changing the type, and you might not want that. Yeah. All right. Any other questions?
How large are the headers, and what are the compile time costs?
Yeah, the headers are not large, but yeah, there is a. It's not a problem for us per se, but yeah, you are dealing with templates, and if you have a lot of these, then they're gonna recurse down, and it's going to be yeah, there are going to be some extra compile time for sure. And yeah, another question. Yeah. 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 I actually, there was a slide missing. I was prepared for another question, which was the runtime overhead. And actually, I don't have it here, unfortunately, but if you, let's say if we can, let's see if I can find it. We have a couple of minutes. Yeah, so this library, CPP bits, so we use the same kind of underlying mechanism. And This guy has a talk specifically on his library and the exact way he's using this exact method. And he goes into the actual runtime implications of this. And his claim is that it's zero overhead, so that it's actually doesn't, well, it's the same as writing it by hand. But of course, that inlies or relies on inlining. So if you don't, like, it has to be header only for all of this to be inlined, and even that might not be enough. So we have this deep kind of trees, then you may not get the inlining. So there you can use some force inline, which is also non-standard, but actually force the compiler to kind of work through everything and actually figure it out. And if it does that, then it becomes very close to zero overhead at runtime. But the compile time suffers. So. All right. Anything else?
So you used exceptions for range checking.
Yeah.
Are any alternatives to clamp them, or what would you?
Yeah, you can have different. That's also, you can. I had this valid range, and you can have a different one, which is like a clamping range or whatever. And so again, you can control that as well. And one thing I didn't talk about is that even if you don't care, if you're just serializing to a binary archive, you don't care about the field names. It's still having the field names there is really helpful to generate nice error messages. And so what you can also do is, I have kind of left it out, but because all of these save and load goes through the same kind of funnel, the same function, you can have a user-facing save and load, which is just what I showed you, but then you may have internally a save and load which has a little context. So it's just a struct, and it doesn't do anything except push and pop back every time you call it, so that you, in any kind of, if you add a breakpoint, for example, you know exactly that you are on the 5th index of this array, and you can get the full context. And then you can also do that for error messaging as well. Like you can make, and also you can do in that context, you can put warnings essentially. So you may load a big struct, and there are 5 things that are not exceptions, but there are not ideals. Like maybe you clamped a number or something. You can put that in the context. So that's nice because everything is kind of funneled through the same save and load. Yeah. I think there was a, yep.
How do you handle erroneous logs? Let's say you serialized beforehand.
Yeah.
You made a change in your library, so now your struct has an additional.
Yeah. In our case, we don't at all. So you can do this if you use something like a schema-based. You can add a since this field was introduced in this version, and then you can get all of that generated before you. But then you lose this kind of specific things. But yeah, that's a problem. We typically in our data formats we have we have a save and a load, or we use this for save and load. But you also have a check, which is just takes whatever binary data you have and check whether it is of the proper type. So a single sensor may push out 100 different types of messages, and they typically have some header that you can use. So if you have specific information in your data, then you can kind of do that, and then just you're not allowed to call a save and load if the check kind of fails. But yeah, short answer is we don't. All right. Anything else? I think that's it. All right. Thank you. Yeah, thanks. Thanks a lot.
I've seen something like that before.
Yeah?
And actually, I'm doing the similar things in my place.
Maybe
But I didn't know about that Zippy library.
Yeah,
I thought the Boost PFR was the first who invented it.
I'm not sure. Maybe I don't know which came first.
Yeah.
But the CPP is it doesn't give the field names. It just does the standard kind of thing.
Yeah. No,
But,
Boost PFR
yeah.
originally was C++14.
Yeah, I know.
solution.
Yeah,
And it also didn't give you the names.
and it's quite recent actually.
Yeah,
because
it's
it,
C++23 who gave it.
Yeah. And I think it was like Boost like 184 or something. Like it's fairly recent in Boost as well.
It was originally called Magic Get Library.
Yeah, really? Okay.
Yeah.
I've heard about that, but I never used it.
Yeah,
So that was kind of
that
put
was
into
original, and there is a CPP con talk where the dude explains how to do that. And speaking of compile time, in C++ 14 there was a lot of templates involved.
Exactly.
Creating new types, which was very slow.
Yeah.
If const expert
it's really
save
fast.
a lot of fast time.
I really like this. I mean, we have a lot of code that is like C++ 17 and prior, and you have to do all this kind of this magic thing where you have, and if const expert, what is really nice is that you can disambiguate. So if you have a lot of different ways of doing it, you can have like this is the first priority, this is second, and it's great.
Well, in my case, we have a RPC system based on structures.
Yeah.
Basically, you say, oh, I have a method. I have a this is what I basically gRPC, but in C++, and then you use boost pfar and all these tricks to generate all the.
And can you get because what they use internally, these kind of macros, can you kind of hook into that so you can get like in the boost pfar, so you can, if you have a method, can you get the signature out of that?
Not a method, but we kind of we pretend to be methods, but it's a fields which we just wrap in special call type methods.
Yeah, exactly.
Which could be invocable. And then you can use the function traits to get the arguments, and then you again boost pfar, and that works.
That's really nice. And you do that at like a large scale?
The RPC itself is only like let's say piloting.
Yeah.
But we also use that boost pfar specifically. We have a module-based architecture, so you can say, I have a module. If you want, I can show you. It's not a secret.
Oh, nice.
And I gave a talk last year about that as well.
Oh, that's cool.
Vi går på hotellet vårt og ser om det er plass der.
På andre siden? Ja. Er det lunsj nå, ikke?
Ja.
Ja.
Ikke gå på do nå.